potential work and free energy. We're going to look at standard reduction potentials. You can find this on your cheat sheet. I think that's actually the first page that has all the reduction reactions. Or you can look in your textbook. All half reactions are given as reduction processes in standard tables. So you can find yours at table 18.1 on page 829 of your textbook. It's actually a bit more comprehensive than the one they give you on the AP exam. There may be some homework questions in which you'll need to use the chart in your textbook as opposed to the one on the cheat sheet. Although, get used to the cheat sheet because you will have that as reference. These solutions that are made here in the standard reduction potential chart are 1 molar, 1 atm pressure, and 25 degrees Celsius. And this is the amount of voltage that can be produced as a result of this particular reduction reaction. And remember, reduction reaction, redox, or Leo the lion says grr, gaining electrons is reduction. So this is telling us the ease of gaining electrons. So for example, fluorine has a great ease of gaining electrons because it's highly electronegative, and its voltage is 2.87, whereas lithium, all on the other end, is negative 3.05, because lithium tends to lose electrons, and so those active metals tend to be on the bottom of the reduction half reaction chart. When a half reaction is reversed, the sign of E0 is also reversed for the voltage. So if we flipped around lithium, which is negative 3.05 on the standard reduction potential chart, and we had lithium producing lithium ion and an electron, the voltage would be positive 3.05, kind of like delta H when you flip things around. However, when the half reaction is multiplied by an integer, the E0 remains the same. So even if we had 2 moles of lithium and we flipped the sign to be positive 3.05, the value of the voltage would still be 3.05. Doesn't matter if I have 1 mole, 2 moles, or 20 moles of that particular substance. A galvanic cell runs spontaneously in the direction that gives a positive value for E0 cell. So in other words, if E0 cell is positive, delta G is negative because these are spontaneous. And that will become important to understand later because, as you'll look on your cheat sheet, there's a relationship between delta G and spontaneity and E cell. So let's look at an example here. We have iron and copper in this reaction. And if we write out the half reaction, which I'm sure you can get, this is what you would have. Notice you'd have to multiply through by iron with an integer, and you'd have to do some flipping around to make it work out. But the two half reactions that are listed here would be as you see on page 829, because here's the voltages. Sometimes it's just easier to look for the voltages because they go in descending order. To balance the cell reaction and calculate the cell potential, we must reverse reaction number 2. In other words, if I only knew this particular reaction, of course I would write Fe plus 3 becomes Fe plus 2. And then I would say copper becomes copper plus 2. And of course electrons are involved and so forth. Do you notice how the second reaction, to make it look like the one we'd like, has to be flipped around? So what happens to the value of E0? Hopefully you said it also has to change the sign. And indeed it does. Each copper atom produces 2 electrons, but each iron only accepts 1. Therefore, reaction 1 has to be multiplied by 2. Think about the idea that we need 2 electrons here. however, do nothing to the 0.77. So what's the overall balanced cell reaction? Well, this is the cathode and the anode. So the balanced reaction is that one. There's the balanced equation. Notice charge 3 times 2 is a positive 6. This is a positive 2. And this is a positive 4. So we're checking that, yes, indeed, the charge equals each other on both sides. But what's the potential? They say cathode minus anode. Or essentially what you do, I don't think of it like that, minus E anode. You can do it that way if you want to. Or I simply just add the two numbers up. Once I've flipped the sign, I've taken care of making the anode sign change. If you follow this reaction and you put in negative 34, you're going to get the wrong answer. So essentially, once I have flipped the sign, I just add, and therefore this would produce 0.43 volts if we hooked this up in a galvanic cell. Now, there's a shorthand way to write this information. Instead of showing a huge, porous disc or a salt bridge and two beakers, we use what's called line notation to describe electrochemical cells. The anode components are listed on the left, and the cathode components are listed on the right, and they're separated by double vertical lines. These double vertical lines are supposed to kind of represent the salt bridge. The concentration of aqueous solution should be specified in the notation when known. So here's an example. Magnesium solid is placed in magnesium solution. So if we're going to think about it in my perfect drawing, I might have some MgSO4, well no, it's a 2, MgSO4, and a piece of magnesium metal hooked up, here's my porous, we'll call this the porous disc, to another one. It has some Al2SO43, aluminum sulfate, and in that one we have some aluminum metal, and that is connected. The anode compartments are listed on the left. Remember, this is where oxidation occurs, and this is where reduction occurs. Anox, red cat. So the concentration of the aqueous solutions must be standard if it's not given. This double line here in the middle kind of represents this. So on one side of the reaction we have this, and on the other side we have that. It's just a shorthand way to write it. Oops. And so I better erase it. Didn't realize there was more they were going to tell me. And yes, you can see that that's the anode and that's the cathode. The anode's always the one that gets flipped around because the anode is where oxidation occurs, and the standard reduction potential charts that you see in your textbook or in the cheat sheet show electrons as reactants. Here, of course, the electrons are products. So the cell potential is always positive for a galvanic cell where E cell equals the cathode minus the anode in the balanced cell reaction. The direction of flow is such where E0 cell is positive. So the nature of each electrode and the ions present in each compartment tell us a little bit about where it's placed in the picture. A chemically inert conductor is required if none of the substances participating in the half reaction is a conducting solid. So you might have a gas that's participating or something else. So you can have an inert electrode, sometimes it's platinum, used for that purpose. So let's sketch a cell using the following solutions and electrodes. Include the potential, the direction of electron flow, labels on the anode and the cathode. Alright, so let's see what we have. We have silver electrode in 1 molar silver ion solution and copper electrode in 1 molar copper plus 2. You notice they're both 1 molar, that's the standard form. Alright, so let's figure out which is which. And sometimes it's easier to figure out which is which when you use your standard reduction potential chart. So I'm going to look up silver and copper. So I'm going to find, here's silver. If I just write down what it says for silver, that's Ag plus electrons yields Ag. And on the chart it says 0.80 volts. I'm going to try to find copper. Where is copper? Copper. And it's a copper plus 2, so we've got to look carefully because we want to make sure we have the right ion. So copper plus 2 electrons yields copper has a voltage of 0.34 volts. Alright, now remember the anode is the one that gets flipped around. And mathematically, you want to make sure when these things add, once one of them is flipped, you're going to have positive E0 cell. Well, that must mean that the copper has to get flipped, because if this is negative and we added, we would get a positive E cell. Otherwise, if we made this one negative, then the E cell would be negative, which is impossible for spontaneous reactions. All of these reactions in galvanic cells are spontaneous. So therefore, this one is the anode, and this is the cathode. So to draw the anode first, because the convention, remember, is to put the anode on the left, and on the right, put the cathode. Think about it as alphabetical. You know, A comes before the letter C. Alright, so in here we're going to have some copper ions, and in this one we're going to have some silver ions, and copper solid is here, and Ag is here. The direction of the flow should be from anode to cathode. And oops, we can't forget our porous disk. That's going to be my porous disk picture. Labels on the anode and the cathode, there they are. And the voltage will be 0.80 minus 0.34. 0.46. So that has 0.46 volts. Let's try this one. Right, zinc electrode in 1 molar zinc and copper electrode in 1 molar copper. So again, we're looking for zinc and copper. So let's find zinc, and I'm going to look for, these are slightly more reactive metals. I see the zinc plus 2. Whoops, and I'm not going to do that. Let's go back. You first go back. Go back. Go back. Here we go. I forgot I had to choose a color. Sometimes these PowerPoints work well, and sometimes they don't. So zinc plus 2 electrons yields zinc is what I'm going to be looking for. And I'm probably also going to find copper plus 2 electrons yields copper. I think I had that one, didn't I? Yes, I did. 0.34. Now zinc is negative 0.76. This is the voltage. So again, one of them is going to have to flip. As you will notice, the one that's lower is the one that's going to flip, the one that's under the other one. So when this works, we have to flip the sign of this one, because if we flipped this, if we made this negative and added, we get a negative number, so it's positive. So this is the anode, and this is the cathode. Anode, remember, is on the left, so I'm going to put my zinc plus 2 and my piece of zinc with my porous barrier there. Whoops, my beakers get skinnier by the minute. And I have copper plus 2 and a piece of copper. And of course it's connected by a wire. Electrons are flowing to the right from anode to cathode. And we have 0.76 plus 0.34, 4, 10, 1.1 volts. Okay, so that's the voltage there. cell. Now let's look at that. What would happen to the potential if you increased the copper ion concentration? Well, let's go back. So here's our reaction. Now I actually haven't written a reaction for this. So if I flipped this around, I'd have zinc. Oh my goodness, I did it again. Pardon me. I'd have zinc yields zinc plus 2 electrons. So that would be the positive 0.76. So if I add these two half reactions together, and the electrons of course are going to cancel, I'd have zinc plus copper plus 2 yields copper plus zinc plus 2. That would be the overall reaction, and that's a balanced reaction because we have the same charge on both sides. Alright, now what does the question say? What would happen if we, let's see, if you increase the concentration of copper ion? So go back to that reaction because I have to see it. So if I increase, and I see it will not let me write, so here we go. What if I increase the concentration of this? Think of Le Chatelier's principle. What if this increases? Which way will the reaction move, shift to adjust? Hopefully you're all screaming at the screen and saying, oh, it's going to shift to the right. And it does. So what will happen to E0 cell? Therefore, if the reaction's going more to the right, we're producing more voltage. If we're producing more voltage, what's happening to E0 cell? Well, let's find out and see what it tells us. The cell potential should increase because if we're producing more voltage, it's going to increase. If you produced, however, in that previous reaction, if we increase the concentration of zinc, the reaction is going to move to the left, and the cell potential should decrease. Work is never the maximum possible if any current is flowing, because that's what energy is being used to do. In any real spontaneous processes, some energy is always wasted. The actual work realized is always less than the calculated maximum. And then free energy, directly related to the free energy difference between the reactants and the products in the cell. We can calculate the spontaneity of a particular reaction by this formula, delta G equals minus NFE, where F is a Faraday. It's how many coulombs per mole of electrons can flow, and that's 96,485. You should find that on your cheat sheet because that is given to you. N is the number of moles.